Hello. Today I'm presenting our SOC analysis capstone project titled Cyberattack Detection and Response using the CIC-IDS 2017 dataset. This is for Team 1. Sophie Samuels conducted the investigation. Eryhnn Douyon analyzed the results and created a rough draft of the slides. Sophia Camacho edited the slides to include all analysis and recorded the presentation, and Michael Samuels helped with all of these steps. In this project, we investigated network traffic data to detect cyber attacks and respond to them using a structured incident response playbook. Specifically, we used the NIST Incident Response Framework to guide how we analyzed and responded to threats. Our goal was to simulate what a real security operations center analyst would do when analyzing threats, while also clearly communicating our findings and decisions. We chose this dataset because it provides realistic network traffic with both normal and malicious activity, allowing us to explore real-world attack behavior and apply our analysis in a meaningful way. So what did we actually do? We analyzed network traffic using SIC-IDS 2017 and identified cyber attacks such as DOS and brute force attacks. To guide our investigation, we used the NIST Incident Response Framework as our playbook. We chose this playbook because it provides a structured process: preparation, detection, analysis, containment, and recovery, which mirrors how real SOC teams respond to incidents. This made our analysis not just technical, but realistic and structured. Onto the dataset. We use the SIC-IDS 2017, which contains both normal and malicious network traffic. It includes attacks like DOS, DDoS, port scanning, and brute force attempts. Before analyzing the data, we had a few hypotheses. First, we expected that most traffic would be normal, since real networks are mostly benign. Second, we expected DOS attacks to stand out because of their high traffic volume. Third, we expected brute force attacks to show repeated login attempts. These expectations helped us guide our investigation. To analyze this dataset, we needed to use several tools. We used Wireshark to analyze packet-level data, which gave us detailed insight into individual communications. We used Splunk as our SIEM tool to analyze patterns across large amounts of network flow data. We also used VirusTotal and Abuse IPDB to check whether suspicious IPs were known to be malicious. We chose these tools because they combine deep technical analysis with real-world threat intelligence, which is exactly what SOC analysts rely on. When we analyzed the data, we compared our expectations to what actually happened. As expected, most traffic was benign. However, we found that DOS and DDoS attacks appeared very frequently, confirming our hypothesis about high-volume traffic. We also identified multiple attack types, including port scans and brute force attempts. One interesting finding was just how dominant DOS-related attacks were compared to others. This shows how common and disruptive these attacks are in the real-world environments. To really understand the scope of the incident, we identified key assets involved. We looked at source IPs, which represent potential attackers, and destination IPs, which are the targeted systems. We also analyzed services such as HTTP, FTP, and SSH to see where attacks were focused. This helped us determine what systems were affected and how attackers were interacting with them. We then went and analyzed the impact of these attacks. DOS and DDoS attacks were classified as high severity because they can shut down systems and disrupt availability. Brute force attacks were medium severity since they attempt unauthorized access. Web attacks were medium to high severity due to potential data exposure. Overall, the most critical impact we observed was the risk to system availability and access control. This step helped us prioritize which threats needed immediate response. In our threat intelligence phase, we identified indicators of compromise, or IOCs, such as suspicious IP addresses and abnormal traffic patterns. We also identified attacker behaviors, or TTPs. For example, High traffic volume indicated DOS attacks, while repeated login attempts pointed to brute force attacks. The threat actors in this case were external malicious IP sources attempting to overwhelm or gain access to systems. We validated these using VirusTotal and Abuse IPDB. This allowed us to connect raw data to real-world attack behavior. After identifying the threats, we moved into remediation. We recommended blocking malicious IPs to stop attackers. We suggested implementing rate limiting to reduce DOS impact. We also recommended account lockout policies to prevent brute force attacks. Additionally, deploying IDS and IPS rules would improve detection, and enhancing SIEM monitoring would improve response speed. One major weakness we identified was a lack of rate limiting and automated detection, which made the system vulnerable to high-volume attacks. For this project, we documented all our findings, including attack types, affected systems, and observed behaviors. We used tools like Google Docs and Jupyter Notebook to organize our work. This step is critical because documentation ensures incidents can be reviewed, improved, and communicated effectively, such as I'm doing now. It also aligns with real SOC workflows. In conclusion, our hypothesis was mostly correct. We expected DOS attacks to dominate, and that turned out to be true. One surprising finding was just how frequent and impactful those attacks were compared to others. From this project, we learned the importance of playbooks and guiding structured incident response. We also gained experience analyzing real-world data and understanding attacker behavior. Most importantly, we learned that documentation and communication are just as important as technical analysis in cybersecurity. On behalf of me and the rest of my team, we hope that you have a wonderful rest of your day, and thank you very much for your time.